Higher derivatives and concavity. The derivative df of a differentiable function f is also a function. Assuming that this is still differentiable, we can form the derivative d squared of f of the derivative of f df. This is called the second derivative of the function f. This can be repeated to form higher derivatives. The notation for the second derivative is f double prime x d squared fx dx squared, capital D squared f within parentheses or without parentheses. The general nth derivative of a function is denoted by f and then in superscript n within parentheses x. dn fx dx to the power n, capital D to the power n, f within parentheses or without parentheses. And for notational convenience, there's a special case. The zeroth derivative f, and then in superscript 0 within parentheses, is the function itself. Higher derivatives of polynomials are polynomials of lower degree. For example, the derivative of the polynomial x to the power 5 minus x to the power 4 plus x is 5 times x to the power 4 minus 4 times x cubed plus 1. And the second derivative of that polynomial is 20 times x cubed minus 12 times x squared, and the third derivative is 60x squared minus 24x. The fourth derivative is 120x minus 24. The fifth derivative is 120, a constant, and all the other higher derivatives then would be 0. So in this case, when we differentiate polynomials, we get simpler polynomials, that is, polynomials of a lower degree. But we may observe that the coefficients get much larger. So for the original polynomial p, we had just coefficients 1 and negative 1, so x to the power 5 minus x to the power 4 plus x, and the coefficient of the fourth derivative was already 120, that's the larger coefficient. So these coefficients may get large as we compute higher derivatives. For the exponential function and for the sine function, differentiation is particularly simple. The derivative of the exponential function is the exponential function itself, and therefore all the higher derivatives of the exponential function are the exponential function itself. For the sine function, we know that derivative of sine is cosine, therefore second derivative of sine is derivative of cosine, that is negative of sine, and the third derivative of sine is negative of cosine, and the fourth derivative of sine is sine itself. So then the cycle repeats and we may form all derivatives of sine easily. The same would apply to the cosine function. Higher derivatives may get complicated. Here I consider the function sine of x squared. Its first derivative is easily computed. It is 2x cosine of x squared. The 10th derivative, however, is already quite horrendous. It starts minus 1024 times x to the power 10 sine of x squared plus and so forth, and then eventually we have 30,240 times cosine of x squared. So this has many terms. Some of them have been omitted, and the coefficients of these terms get very large. The function defined by the expression e to the negative 1 over x squared when x is different from 0 and 0 when x is 0 is particularly interesting. The graph of this function f looks like the cross-section of a bowl. Near the origin, the graph is almost identical to the x-axis, and one can show that all the derivatives of this function at x equals 0 are 0. This is all derivatives of all degree of this function vanish at the origin. The graph of this function has the horizontal asymptote y equals 1, and as x approaches positive or negative infinity, the values of f of x approach 1. Derivatives of this particularly nice-looking innocent function are quite complicated. This is the graph of the first derivative of f, and here y ranges from -1 to 1. Here we have the graph of the fifth derivative. This already looks pretty wild, and y ranges from -5,000 to 5,000. And here is the 10th derivative. Y ranges from -5 times 10 to the power 11 to 5 times 10 to the power 11. So something very special is happening. The original function looked like the cross-section of the ball, smooth and nice, but its derivatives behave wildly. In general, higher derivatives of functions may get very complicated. Here we consider the function e to the negative x squared. This is a function that has applications in statistics. The picture shows the graphs of the function f and those of its fourth and fifth derivative. Fourth and fifth derivative vary so wildly that the graph of the function in this scale appears to be almost the x-axis, which of course is not the case. But the variation in the values of the derivatives are much higher than the variations of the values of the function itself. This poses problems later on when we develop serious expansions for functions. Studying derivatives, we already have established that we may find out whether the function is increasing or decreasing. We may find out more about the shape of the graph of a function studying derivatives. We say that the graph of a function f is concave up in an interval from a to b if the graph of the function stays on or above any of its tangent line in this interval. The green curve in this picture is concave up because it stays on or above any of its tangent line. Likewise, we say that the graph is concave down in the interval from a to b if the graph stays on or below any of its tangent line in this interval. This graph here, the black curve, is concave down because it stays below or on any of its tangent line. Recall that by the mean value theorem we have already seen that if the first derivative of a function is increasing on an interval from a to b, then the graph of the function is concave up on that interval. From this we get the useful characterization: if the second derivative of a function f is positive for all x in some interval from a to b, then the graph of the function f is concave up, because then the first derivative is increasing. Likewise, if the second derivative is negative, then the graph of the function is concave down. So when we have to figure out whether the graph is concave up or concave down, we simply look at the second derivative. Here, this picture shows the graph of a function f. This is the black curve. Its derivative is the blue curve, df, and the second derivative is the red curve, d squared of f. The portion where the second derivative is positive corresponds to the area where the graph is concave up. So the graph is concave up in this region, and the black curve clearly is concave up. If the second derivative is negative, then the graph is concave down, so the graph is concave down in this region. One should observe that the graph of a function may be concave up on an interval from a to b, even if the second derivative takes the value 0 for some finite number of points. An example of such a situation is the function x to the fourth. Its derivative is 4 times x cubed, and the second derivative is 12 times x squared. 12 times x squared is positive except for x equals 0 when it takes the value 0. The graph of the function x to the fourth is, however, concave up everywhere. The word concave is of Latin origin and has the same root as the words cave or cavity. When we are in a natural cave, it feels like we were under the graph of a function which is concave down. Cavities in teeth are also usually concave, like the one shown here in this picture, but they are extremely unpleasant, of course. A point P on the graph of a function f is a point of inflection if the direction of concavity of the graph of f changes at that point. At points of inflection, the second derivative changes its sign. So points where the second derivative changes its sign are points of inflection. This picture shows a graph of a function f, this is the black curve, and that of its second derivative, which is the blue curve. The second derivative changes its sign at the point of inflection. And the tangent line goes through the graph of f at the point of inflection. So these are rather special points. To summarize, to compute points of inflection, one has to compute points where the second derivative takes the value 0 and at which the second derivative changes its sign.